In this video, we're going to look at 11.3 polynomial functions, which focuses on short-run behavior. Starting with example 1, when we investigate the short-run behavior, that's like if we're looking at a zoomed-in version of the graph. So the first thing we're going to do for this function is we're going to factor it. So we are going to factor out the x to get x squared minus x minus 6. And then we're going to factor from there to get x times x minus 3 times x plus 2. This is our u of x function in factored form. We like to factor it because that helps us find the zeros. If you set each factor equal to 0, you will get 3 x-intercepts. They are at 0, positive 3, and negative 2. So in part C, it first asks, describe the graph of u of x. Where does it cross the x-axis, the y-axis, and where is it positive or negative? So here's what we do. We already know where it crosses the x-axis. That is at those x-intercepts. So that is at 0, 3, and negative 2. And to find where it crosses the y-axis, you're just going to plug a 0 into the original function. If you put in a 0, you get out a 0. So that is at the point 0, 0. So I can start graphing this a little bit. I can plot those 3 x-intercepts. So I have 1, 2, 3, negative 2, and then there's 1 here at 0, and then the y-intercept is covered there as well. Now what we're going to do is we're going to address the second part of this question. We want to find where is the function positive and where is the function negative. So we're going to go ahead and make a number line. We're going to do what's called a number line test here. On your number line, you're going to plot all of your x-intercepts, so 0, 3, and negative 2. And then what you're going to do is you're going to choose a value in between each section, and you're going to test it in the factored form. So let me choose a value to the left, negative 5. And then what you do is you take that number, and this could be any number to the left. It doesn't have to be negative 5. And you take that number and you test it in your factors. So think about this u of x function. If I put in negative 5, what would I get? And I don't really care what the numbers are. I just care about the signs of them. So I would get a negative 5 in front, which is negative. I would get negative 5 minus 3, which is a negative 8, which is negative. And then I would get negative 5 plus 2, which is also a negative. And if I multiply 3 negatives together, I am going to get out a negative value. So this section is going to be negative. We are going to go ahead and continue this to test the rest of them. So I'm going to test negative 1, I'm going to test positive 1, and I'm going to test positive whatever, 4 or whatever you want. What should happen when you do each of these tests? I'll go through negative 1 with you. You're going to do this for every single one. Negative 1 should give you a negative, and a positive, so that end result is a positive. If you continue this, the number line test, you should find that the next section is negative and the final section is positive. Now, how does that help me? Well, first of all, this helps me answer where the function is positive. That happens between negative 2 and 0. And it happens again from 3 to infinity. It also helps me address where this function is negative. This function is negative to the left of negative 2. And it is also negative between 0 and 3. So I'm able to address just that aspect of describing the polynomial, but also more importantly, what's going to happen is it's going to help me sketch the function. If I know that the function is negative to the left of negative 2, then that means the graph is sitting below the x-axis. If it's positive between negative 2 and 0, then it's going to be above the x. If it's negative, again, between 0 and 3, it's going to sit below. And if it's positive at the end, it goes up to infinity. Remember, we talked about long-run behavior already. The end behavior of this thing should be the same as the end behavior of x cubed, which goes up to the right, down to the left. Now, when I make this zoomed-in graph, notice I'm not even scaling my y-axis. So I don't know if this point here is really as high or low as it should be, and same with this one, but I am just getting a sketch of it. I'm just checking that I have the correct x-intercepts and that I have positive and negative sections correct. Now on example 2, we've got a new problem here. We've got a p of x function. There's a plus sign missing here on this PDF. Add that in, please. And we're going to use synthetic substitution to find these numbers. If you don't remember synthetic substitution, what you do is you find the number you're plugging in, you put it in the little box, you line up the coefficients of your function you're dividing by. So we have a 4, then a -5, that was supposed to be a 5, then a +7, and then a -9. If you don't have a term, like if you're missing an x term or something, you would put a 0 placeholder for it. To do synthetic substitution, what you do is you add down, so 4 and nothing is 4, and then you multiply back to the original. 4 times 2 is 8, and it goes in the next column. Continue. Add down to get a 3. 2 times 3 is 6. That goes in the next column. Add down to get a 13. 2 times 13 is 26. Add down to get a 17. And this value, 17, is the output from P of 2. Now, why would I do that? It might just be easier to just put 2 into the function. The reason we need to do this is for other purposes. So we first learn here how to use synthetic because we'll have to use this when we're factoring and finding roots. Go ahead and try P of -3 and submit your answer. So in example 3, it asks us to find a formula for the function. So what we are going to do is we are going to work backwards here. We're going to take the x-intercepts that we see. I see one here at -1. I see one here at +3. And we're going to rewrite those as factors, x plus 1 and x minus 3. Now, I'd like to point out here that this is a cubic function. This has the end behavior of -x cubed up to the left and down to the right. So I'm concerned by the fact that I only have 2 factors. There are only 2 roots, but remember, this over here is what we consider to be a double root. A double root shows up in your factors as a factor squared. What happens with the double root is it gets close to the x-axis and bounces off it. It doesn't go through it. Like -1, it just goes right through that portion of the graph. If it's a double root, it doesn't go through, it bounces off. So I just make that factor squared. Okay, now there's always going to be some a that we have to find, and we don't know what it is. We've had this for other functions too. So once you have the factors, you're just going to figure out the a value that makes it specific to your function. To find that value, find another point you haven't used. So like I'll go ahead and use this point here. You can't really read it very well on the PDF, but I will tell you it's 0, -3. And then you can plug that in, -3, and 0, and you're going to solve for a. Go ahead and finish this problem, find your a, and then write your whole equation. And what I want you to type into Edpuzzle is the answer to the function. So after you find what a is, give me the whole equation written out in the Edpuzzle. In example 4, we want to know if either of these are factors to the equation we have here. And on the equation on my PDF, I'm missing a little plus in front of that 3. So to see if it's a factor, one option is I can use synthetic division, and I can say, okay, if this is x minus 1, then the root I'm testing is x equals 1, and I can set this up. But notice, because this is x to the 100, I'm going to have a coefficient of 1, a coefficient of -4, and then I'm going to have a 0 for power of 98, a 0 for power of 97, and this is going to go on forever. So just because you can use synthetic doesn't mean that it's the best option every time. If you want to see if x minus 1 is a factor, just plug 1 in. 1 to the 100 is 1, minus 4 times 1 to the 99 is 1, plus 3. Does it give you out a 0? You're going to get -3 plus 3 is 0. Basically, if you plug that number in and it gives you out a 0, that means the point 1, 0 is part of your function, and that's an x-intercept. If that's an x-intercept, then yes, x minus 1 must be a factor. Go ahead and check x plus 1 and tell me if it is or is not a factor. Now for the real challenging stuff. On example 5, you have an equation here and it's missing some signs. There's a plus in front of the 3x cubed and a plus in front of the 3x. And I'm just going to add in all the signs for all the problems. There's a plus on part B as well, and then 2 plus signs on C as well. So Basically, if you are trying to solve, the first thing I like to do is factor. So on part B, I will be able to factor this. I'm going to subtract the 12 over so that I get something like this. And then what that lets me do is factor by grouping. I can group these two and these two. In the first group, I take out an x squared to get an x plus 3. In the second group, I take out a negative 6 to get an x plus 2. I made a mistake over here. That should have been a 2. My apologies. There we go. And this is equal to 0. Once you have your first two groups factored, there should be a common factor within the two groups. So what you do now is you factor out the x plus 2, which leaves you with an x squared, and then it leaves you with the minus 6. Now I have factored this as much as I possibly can, so now I get my solutions. This gives me a negative 2. If you set this equal to 0, you can add the 6 over, and when you square root both sides, you're going to get two answers, a plus or minus root 6. So those are all of my solutions to part B. Remember, the degree of the polynomial is the max number of solutions. So since this is a degree 3, I'm expecting 3 answers. Now, it's possible some of those are imaginary or some of those are repeated, but if I get 3 answers, I feel pretty good about that. Now, on A and C, I would love to try factoring, but I can't. It's a degree 4. There's no factor by grouping. There's 5 terms. There's nothing I can really do to factor. So instead, I go through the rational root theorem. The rational root theorem says possible zeros are going to be factors of your last number, factors of 4. So that's 1, 2, and 4, divided by factors of your first number. Your first number in front is just a 1. Thank goodness. So my possible zeros, rational zeros, I should say, for this problem are going to be positive and negative 1, positive and negative 2, positive and negative 4. It doesn't mean that those are my only answers. I might have answers that are not rational, like imaginary or with a radical or whatever. But these are at least some of my possible answers, which can get me started. Now for the fun part. You are going to go ahead and pick a number. I'll just pick 1 to start. And you're going to run it through synthetic and see if it's a root or not. Line up all your coefficients, be really careful with your negatives, and make sure if you're missing a term, you leave a space holder for it. And then we go through synthetic. Add down, multiply over, add down, multiply over, and continue this process. And if you get a 0 at the end, that means that your function, when you put in 1, gets you out a 0, which means yes, this is a root. If 1 is a root, then the factor is x minus 1. So then this is the remaining factor. Go ahead and attach the x's back on. This is going to be your constant to the right, so this will be your x, this will be your x squared, and this one will be your x cubed. So this is x cubed and 4x squared and x and 4. The good news is you don't have to do this again. You can now factor this by grouping. Go ahead and factor this by grouping, finish this problem, and give me your answer. I am looking for 4 roots in total, but only 2 of them are real. So expect some imaginary answers here. Go ahead and type those in on your Edpuzzle. For this very last problem, we have the same issue where we can't factor or do anything to start this. So we're going to start by finding possible zeros. Again, to find the possible zeros, you are going to look at all ratios of factors of 2 over factors of 2. So I could have 2 over 1, 2 over 2, 1 over 1, or 1 over 2. If you're asking how I'm getting these, the factors of 2 on top are either 1 or 2. The factors of 2 for the denominator, which come from the front, are either 1 or 2. And I have to do all the possible combinations of that. So 2 over 1, 2 over 2, 1 over 1, 1 over 2. And then I just pick and I test. Little hint here, do not start with positive 1. Let's go ahead and start with positive 2. And if you started with positive 1, you would run through this. You would knock it out of 0. So you'd go, bummer, restart. It sucks. You just have to keep trying until you finally get something. We're going to start with +2. I feel good about this one because I'm cheating a little bit and I already know the answer. So I'm going to drop this 2 and multiply, add down and multiply. Add down and multiply. Add down and I get a 0. What a relief. By getting this 0, this is your remainder. That tells me that when I put in a 2 to the function, I get out a 0. By knowing this, that means that 2 is an x-intercept. And if that's an x-intercept, then I know that it's a factor, x minus 2. Now, the other factor is going to be this. Attach those x's back on. So it's going to be a 2x cubed, 3x squared, minus x minus 1. So what I've done is I have rewritten my very first line in a more factored form. But I got to break it down more. What I did last time was I factored by grouping here. This is not factored by grouping. So that sucks. So what I'm going to do instead is I'm going to have to just run through synthetic again. This time I'm looking at factors of 1 over factors of 2. So my possible roots are either going to be 1 over 1 or 1 over 2. So there's no need for me to try 2 again. That won't go into this. This is not a possible root for this guy. There's no need for me to try 1 again because I tried 1 originally and it didn't work. So I don't need to try it here. It's not going to work still. So let's go ahead and try one of those fractions. Why don't we just try, for fun, -1/2 and see what happens? I am plugging this into just this cubic now. I already have my x minus 2 factor, so I don't need to do anything there. But I'm going to run through the cubic expression. So I'm going to have the 2, the 3, the -1, the -1. And I'm going to drop this through. So we go 2, multiply for -1, 2, -1, -2, +1, I get a 0. Yay. So I still have my original factor. Let's see how much space I have here. Oh, good. I still have my original x minus 2. I took this cubic and I said, well, I've also got a factor x minus 1/2. I'm sorry, x plus 1/2. And then here's the resulting factor, 2x squared plus 2x minus 2. You can go ahead and pull that 2 out. Since this whole thing is equal to 0, you can divide that 2 away technically, which is kind of fun. And you can say that you have just pull that 2 out to get x squared plus x minus 1, and then you divide the 2 away. So you're just totally allowed to ignore it. To solve this, it's not factorable, again, but it is a quadratic. You guys know how to solve a quadratic without factoring. You use quadratic formula. So we go -b, b is 1, plus or minus square root of b squared, 1, minus 4 times a is 1 times c is -1. All over 2a, which is 2. And then you're just going to simplify this down. Inside you get 1 plus 4, so I'm going to call that 5. And there you go. What I would like you to do is type in your answers to this problem. These are 2 solutions. There are 2 other solutions that you found by factoring. Go ahead and type in all 4 answers.